Hello, this is a demonstration video in which we show off some of the features of our particle simulator we created for simulation in computer graphics. We're going to begin this presentation by showing some of the forces that we've developed, namely gravity, springs, angular springs, directional drift, and drag. Gravity is a simple force that acts on all particles and introduces a downward force that drags them down. In the video on screen you can see a small gizmo in which we've chained together several particles using rods, springs, and particle and circular constraints, in which you can see the gravity in action. Springs are forces that act on two particles, which tries to keep those two particles within a certain range of one another, following Hooke's spring law. Depending on how we set the coefficients of the spring, it can either act like a very stiff spring, like for example a car suspension, or more lax, like a rubber band. Using these springs, we can develop cloth-like simulations using the mass spring cloth model, in which we take a lattice of these springs and particles and chain them together. Here you can see what that looks like for a small piece of cloth when there is no gravity and there are no fixed particles to keep the cloth in position. As you can see, the cloth experiences some small deformations from being dragged across the screen, but at the end relatively quickly turns back to its original shape. Here you can see the same piece of cloth, but with two fixed particles constraining the cloth to a position and an added gravity force to make it taper down. Here you can see that the cloth experiences some deformation, especially around the two fixed particles. You can also see how certain velocity changes introduced by the mouse ripple through the cloth. An important thing to note is that this type of simulation has a tendency to blow up when using explicit methods for solving. Therefore, we recommend that you solve something like this using implicit method, like implicit Euler. We also added angular springs, which are forces that act on three particles at once and try and keep a certain angle between the edges formed by the three particles. And here you can see a small demonstration of a hair-like simulation using those angular springs to simulate strands of curly hair. This is a relatively simple simulation, but we've chained multiple angular springs together using springs in between them. Another type of force we added was directional drift, which is a vector field that can be introduced to the simulation by clicking and dragging the mouse across the screen in the desired direction and holding the right mouse button. These forces then get added to the force accumulators of the particles, and the forces from the vector field decay over time. Lastly, we added drag as a general force to the simulation. This is just a simple force that basically removes some percentage of velocity from the particles from this current iteration. This, as the name implies, causes small drag on the particles in the simulation, causing them to not move indefinitely and will eventually come to a halt. We added this for some extra realism and also to smooth out some of the drifting and floating point errors that occurred in the simulation, especially rounding when the system would become more stable. We're now going to showcase some of the constraints that we created for the particle simulation. In particular, we're going to talk about circular constraints, rod constraints, and line constraints. Circular constraints act on a single particle and restrict the movement of that particle to the circle that it's as defined as, given its center and radius. On the video you can see how a particle that's dragged along by the mouse can only be dragged along like a bead on a string. It does not come off of the circle. Rod constraints, like spring forces, act on two particles and enforces a set distance between those two particles that they have to adhere to at all times. We also added line constraints, which act on a single particle and restrict that particle's movement to a line. The particle can then travel up and down this line, sort of like as if it were on a rail. Lastly, we implemented several methods for solving a system. In particular, we've implemented explicit Euler, the midpoint method, Runge-Kutta-4, and implicit Euler. Finally, we wanted to show you the effectiveness of several of the integration methods when integrating a system consisting of a mass spring cloth model with its two top corner vertices attached to a fixed position. You can see how the explicit methods, such as explicit Euler, midpoint, and Runge-Kutta-4, have a lot of difficulty stabilizing the system and tend to explode very quickly. Meanwhile, the implicit method, implicit Euler, is much more stable.